Hi everyone, I'm Silba Dowell, and today I want to talk about benchmarking agentic workflows with Charliecloud. So here's a quick overview that I want to cover today. First, we'll go over the background, what my job title is and things like that, the motivation of what this project is about. Dragoon is my benchmarking suite that I'm incorporating Charliecloud with. And then Circe is an internal HPC AI framework that we've developed at Los Alamos National Lab, setting it up with Charliecloud, and then finally future directions with this project. So for the background, where am I coming from? Well, so I am a AI HPC engineer at Los Alamos National Lab, and my job role is I intersect between users, stakeholders, and AI HPC practitioners. And most of the time what I'm looking at is multi-physics codes, AI workflows, and between those two, I'm trying to figure out how can I integrate them both together and help users when it comes to optimizing their codes. And that could be through infrastructure or algorithmic means. And so the motivations for the project that I'm going to cover here in a few seconds is that I noticed there was a bit of a gap. And so currently what it seems like is that there is HPC AI benchmarks that focus on the model performance on hardware. And there's also benchmarks for the model evaluation, the quality of the AI model itself. But there seems to be something missing with these specific types of infrastructure that these models need support for. So this is like either having your model set up on-prem, locally in some directory, or what I want to focus on more specifically is model endpoints. It would be really nice to get a test benchmarking suite that was centralized on model endpoints in particular, so that admins, HPC researchers, and users who want to diagnose their workflows could benefit from something like that. And how would they benefit? Well, so here, what I have is a diagram that lays out what I like to call the anatomy of how these AI workflow infrastructures typically operate. So suppose that you have several users that want to use an AI model. Well, to route the requests, to try to organize every single API call each user is going to send to that model, it gets very complex, and you want to try to optimize the HPC hardware so that is efficiently using that LLM in the back end. So in between where the user sits and where the hardware sits to support that LLM, we have an AI gateway, a router essentially, that tries to make sure that if you send off HTTP requests, there's some load balancing that's set up, and the LLM in the backside on the GPU node is able to process those requests efficiently and as best as it can. Well, you might see here, in this anatomy, there are several different kinds of bottlenecks that could potentially arise. So maybe there could be something even at the front level, at the user-facing level. And so it would be helpful to know, okay, what could happen? What are the possibilities with having this sort of setup? If you have an agentic workflow, is the agent constantly trying to retry its API calls, or what is going on? Well, then there's also a different layer. So this is the latency portion. When we think about model endpoints, you're trying to send API requests to a server. So there is some sort of time factor that you have to take into account with that. There could be potential bottlenecks there too, depending on the network. And then finally, I ask myself, well, what's going on in the hardware? Because what if perhaps something got configured in the back end And it might make the inference engine server that the model rests in the GPU not perform as efficiently as you are wanting. And so with that, this is something that I've been working on. It's called Dragoon. And Dragoon is a job class from the video game series Final Fantasy, if you've played that. And what it is, what I hope to achieve, is an agentic end-to-end benchmarking suite. And so the idea here is that I want to capture benchmarking and target those AI gateways for routers such as LiteLLM, but there's also competitors like Kong, I think, is a recent one. And so not only do I want to look at the model endpoint performance, but I also want to see what the GPU is doing if you send prompts in the back. So with this, the target is also trying to assess realistic AI ModSim RAG workflows. And if I can figure out a way to set up a agentic workflow that maybe is trying to do domain science tasks, and I work with users and try to see how are they actually using agents rather than what I think they should be using, well, then I could apply this to somewhere else on a different system and see what is the reality of how our HPC systems are used, how the model endpoint getting used. So this is a little different from Stream or HPL, common AI ML benchmarks you've probably heard of, because those benchmarks focus more, as mentioned previously, the performance of the model directly on hardware through computations. So linear solvers or matrix multiplications and things like that. So Dragoon is a little different. And so here's the tech stack. Right now, it is using Charliecloud as a containerized workflow. And on the left here, this very nice, beautiful looking bear is Ursa. And this is our public framework that is a agentic service. You can call agents to do reasoning or other domain science tasks. The inference engine server that sits at the GPU node is vLLM. And then if, for instance, maybe you wanted a UI, commonly, if you're setting up a server, some users do like that UI experience. Well, so there is some benchmarking for OpenWebUI as well. The last two here are addressing the GPU profiling part and more recently developing the model context protocol. So for GPU profiling, that's Insight Systems. For MCP servers, model context protocol has some potential avenues to benchmark. And so now I want to cover metrics that I gathered very recently. These are preliminary results. So to just make you all aware, I haven't been able to fully analyze them yet or understand, interpret them very well, but I do want to point them out still because I think it's important. So what's going on here? Well, I set up a self-hosted online server model endpoint with GPT-OSS 120B. And the way I did that is I just allocated myself a GPU node, and on that node, I stood up an inference engine server, vLLM, put GPT-OSS there, and then I opened another shell and tried to act like I was a client, and then send those requests back and forth. And during this time, I sent out 10,000 requests in total, and as you can see here on the left, there was about 9,861 successful, but some did fail, so that seems pretty good as a result that was just me kind of playing around. I did put this setup, this benchmarking test, with a parameter of 100 requests per second. So that means concurrently, each second, 100 requests are going through to that model endpoint. So from that, what I found was that throughput was about 51 requests per second, peak concurrent requests 6,767. Okay. Now looking at token generation, this is just talking about that model itself in the back end. How many input tokens did it receive? What were the generated tokens with the response, the output token throughput? So these are pretty big numbers. I believe the reason why, I would have to do some digging, but I think it's because when I set up my self-hosted online server, it was just directly with that GPU node. So there wasn't that much latency because I'm still on that same system, I'm still on that same node. It's not like I'm going to a totally remote server on a different system. So I think that might be the cause for what you're seeing here. Well, finally, there's response time, right? Because again, I want to try to simulate what it takes for requests to go through a model endpoint. I really care about latency. And so similarly, the time to first token is super fast. It is 64,943 milliseconds. And time per output token is 179 milliseconds. Inter-token latency, about 60 milliseconds. So now I want to talk about an internal LANL tool we've been developing. It's called Circe. And the reason why I want to bring it up is because Circe is in fact our attempt to make a model endpoint service with a UI. So it does rely on LiteLLM. It relies on Open Web UI for that front-end experience. And it does use vLLM so that it can support that model in the back end. And you may notice here that Dragoon kind of follows what Circe's doing. And really, that's just because, well, at the time, we were trying to figure out how to stand up Circe. So when it came to the benchmarking piece, naturally, my colleague, he's the main developer of the Circe tool. He came up to me and was like, hey, we're trying to test this out. We're still kind of in the prototype phase. You said you've been looking into benchmarks. Can you kind of check some stuff out for me? And I said, yeah, of course. Well, so I realized that because now we have Circe in its beginning stages of production, it'd be really nice to be able to capture similar metrics, follow the same style, the same tech stack as what Circe had. Of course, in the future, I would like to make Dragoon more generalized, but I think that's something that I'll have to work on pretty hard. I'm basically the only one working on this, so it's going to take me a bit. Well, now I want to move on to the Circe model endpoint metrics that I gathered using the same procedure with vLLM bench. So now you can see the metrics look a little bit more realistic, not like 65K whatever. Well, so during this time I sent 1,000 requests. Request rate was really high, is 200 RPS. But I think what's interesting here is the request throughput and peak concurrent requests. And I bring these metrics to your awareness because this is the result I got when stress testing Circe when it was still in its prototype stages with its associated hardware. And when I ran this stress test, this is when Circe unfortunately had a bit of a trouble handling those peak concurrent requests. So there was a bottleneck, right? There was a bottleneck, but again, I talked to my colleague, the main developer of Circe, and he goes, oh, this is really fascinating, actually. Like, this is a great scaling study we can do to find potential bottlenecks this way. And I said, yes, I think so too. Like, this is really cool. These other metrics here, I won't go over the values anymore because you can read them off the screen. But maybe I should cover what they are trying to target. If you aren't too familiar with how this tokens and latency works, GPT OSS 120B has its own tokenizer. It's the Harmony tick token thing. And so when a prompt gets sent to that model, the string that's getting sent has to get chunked up somehow. It has to get encoded. And so GPT-OSS relies on byte-pair encoding. It's just a particular type of encoding framework. And so that's why when the model receives that tokenized input, then that's when it tries to formulate that response and output the response request back to the user. So now let's talk about the Charliecloud part, because this is a Charliecloud talk after all. Here are some things that I noticed when I use Charliecloud, what I think is awesome about it, especially for my project. I would say that Charliecloud is very reproducible. It's easy to set it up in different systems because it's not privileged, or as privileged maybe as other services that I've seen or have discussed with colleagues. So if I need to work on system A and then I'm thinking, oh, I want to recreate the same trial run with Dragoon on something else, then I just take Charliecloud, I'm like, boop, I put it somewhere else, and then it's very easy to set up. So there's that part. Okay. The other good thing that I like about Charliecloud is that you can deploy it on secure systems. And we do have those at Los Alamos National Lab. And so why not Docker or Aptainer? I do believe that perhaps Docker and Aptainer do have functionalities that may be interesting for me to explore. At the time, though, what I was able to grab off the shelf real quick was Charliecloud. So there was that user-end experience that I enjoyed. It was very easy to understand what the commands were doing from a user perspective. I'm sure the back-end development is very complex, though, and I appreciate that. And so, yeah, Charliecloud was very easy to onboard. It's daemonless, which is a plus for secure systems also. You don't have some invisible running background process trying to do stuff for you, because that would be kind of like a security risk, right? And so here is that code or command I ran to do my benchmarking. It is rather large, but it's really just because I'm doing vLLM bench. So vLLM has their own benchmarking commands. And so really the only Charliecloud bit I had to do was just setting up environment variables that were catered specifically for GPT-OSS. GPT-OSS is kind of special compared to the other GPT models. It requires a bit more steps to stand up. And so here you can see that my base URL was just like a local server on some GPU, allocated GPU. And then I did use a data set, this shared GPT data set that is just random prompts, string text, queries that you may see as a normal user. And number of prompts was 1, request rate, well, that's 1. Well, actually, this is not quite realistic. I was tuning this to how I wanted to see that scaling study, right? But this is just me when I ran this command to try to figure out first time, how do I use this thing? So with that, I'm going to cover now future directions on what I want to do with Dragoon. So with Dragoon, I would hope to achieve a report module, get logs, get plots, try to see, okay, if I'm using different microservices or using specialized infrastructure, what are they telling me? I want to put it also in a single spot. So I want to aggregate that data. Finally, with agent tracing, it would be really cool if I ran some agentic framework like LangChain, or in our case, Ursa, and I get to see what that agent was doing the entire session that I'm trying to benchmark or stress test. And then finally, because MCP is now getting very, very popular, well used, MCP has benchmarking capabilities. I want to see what is the agent doing there too. And so I'm going to end it off here, and I hope you enjoyed my presentation, and if you have any questions, just let me know.
Thank you for the presentation. My question is that you have the performance evaluation that you did. I just wanted to know how that maps into the anatomy that you explained before for the model.
Sure. So, I have to answer through the microphone. Yes. Okay. Yeah, that's okay. Right. So, in that real case with the Circe model endpoint, I discussed that, hey, this is when we noticed that Circe was breaking down. We were stress testing it. So when you do go look at the anatomy, I would say it's in this section 2 region. So that was the latency part. That's when I sent off all those requests at the same time, the UI, that open web UI part, you couldn't access it. It was just like a blank screen for like, I don't know, 15 minutes or something, kind of insane, you know? And then even the API through LiteLLM to send requests, you don't do UI version, right? That also wasn't working. So that's why it was so interesting when I was talking with my colleague, and then he comes back to me, he's like, hey, I'm looking at the logs, and I think you broke Circe. And I was like, oh, I'm sorry, but that's cool, you know? So I like that. And he said, I like that too. So there you go. Yeah. Any other questions? Travis. Oh, yeah, that's right. Okay.
Similar problems in other rooms.
That's okay.
So from your perspective, you're like sending API calls to some endpoint or clicking like on a web page or something, and you might know where this model is running on the hardware because you have insider information at the moment. But in the future, you may not have any idea where this model is running or what hardware it's on, right? So is there any way you could, like, I don't know, we have a mix of newer, faster GPUs and a mix of slower, older GPUs, and LiteLLM may not distinguish between the two. So how would you sort of, I don't know, account for that in your analysis of your benchmarks?
So you're saying, oh.
Yeah. Yeah.
Okay, so you're saying you care about LiteLLM possibly changing to something else, or are you curious about GPU, or you're curious about everything?
I'm saying from the user side.
Yeah.
You have no knowledge of where this model is running.
Yeah.
So it could be on like an old A100 or a new H200 or whatever, right? And those performances, what? AMD? Yeah, or AMD. Yeah, sorry, NVIDIA shop. But so you don't know like what hardware this model is going to be running on. So the performance might change depending on which model LiteLLM hits.
That's a good point, and I understand what you're saying. I thought about that too. And so that would probably get integrated with the report module. So I would basically try to gather, NVIDIA-SMI, what's the GPU in the back end, and then, all that kind of stuff. So.
And I mean, it could also be a LiteLLM feature, right, where only send my request to models running on this hardware.
Maybe, yeah. I don't know, do you know if LiteLLM does that? Oh, okay. But then maybe Dragoon can add on to that. So, any other questions?
It's coffee break time, so if you have questions, ask her during the coffee break.
All right, well, thank you.